actually think we have the core group, so I think we can get started.
Okay, good. All right, thanks everybody for joining. My name's Anthony Partridge. I work at Genentech, and I'm also on the PDHC leadership team. I'll be monitoring today's discussion, and so I'm really delighted to have this really great panel of speakers today. Hopefully everyone's had a chance to view their seminars. I will ask them to just very briefly summarize what their seminars were about in a minute. But I thought I would just introduce the panel. So we have Hannes Stark from MIT, and Stephen Reddy from Bilia, Yu-Shan Lin from Tufts, Vikram Mulligan from Flatiron Institute, and finally Parisa Hossainzadeh from University of Oregon. So the agenda today is in a minute, I will ask each one of the speakers to, within 1 minute, to summarize what their webinar was about. And so this will be, what problems did the work address, and how did they move the field, right? So in other words, what were the main outcomes of the work they presented? And then we'll move on to a moderated discussion led by me, and so there'll be 3 topics, each roughly 12 minutes. And each one of these will be focusing on ultimately how do the advances that were presented help us design new molecules and move us towards a clinical candidate. That's ultimately what we're interested in. And so I'll frame this a little bit in terms of the impact on the design, make, test, analyze cycle, so the DMTA cycle. That's obviously a little bit of industry terminology, but what that means is, you want to shorten the time from designing a molecule, making, testing, and analyzing it as short as possible so that each iteration of that cycle can be as quickly as possible so that we can get to the finish line with the fewest number of molecules and with the greatest speed. And so, at least some of the conversation, I'll ask the speakers to think about that question and address it. And then finally, in the last 15 minutes, we'll be taking questions from the audience. So if you have questions, please just put them into the chat. Feel free to put them as they pop into your head, and I will select several of them for discussion during the last 15 minutes. So with that, I thought we could just go to each of the speakers and ask them to introduce themselves and summarize their seminars. So let's start with Hannes. You want to go ahead?
I'm a PhD student at MIT, advised by Regina Basler and Tommy Yakula, and I work on generative models for biomolecules, I would describe.
Great, thank you. And Stephen.
Hi, I'm Stephen. I'm a scientist at Bilia, received my PhD from Gaurav Bhardwaj's lab at the UW. My seminars were about application of a cyclic offset to try to utilize the deep learning models that have advanced protein binder and structure prediction so much for cyclic peptides. We showed validation both in terms of designing binders as well as the accuracy of those binders by X-ray crystallography.
Great.
I see. Then sorry, I guess I understood that wrong. I should also say my stuff was about PolsGen, our new binder design model, where we then design nanobodies, proteins, peptides against various targets and have experimental validation across 26 targets.
Great, thanks for that. Yu-Shan.
Hi, it's Yu-Shan Lin at Tufts University. So my seminar is about that for a lot of cyclic peptides, they are now well structured. And so how we can use molecular dynamic simulation to actually sample the Boltzmann distribution and, for example, use this information to help design cyclic peptides that best pre-organize in solution for specific mimicry or binding toward targets.
Okay, great, thank you. Let's move on to Vikram.
I am Vikram Mulligan. I co-head the Biomolecular Design Group in the Center for Computational Biology at the Flatiron Institute. My seminar is about a pipeline that I work to develop for physics-based design of peptide macrocycle therapeutics and the successes we've had, as well as ongoing work to improve the accuracy, generality, and tractability of the pipeline by bringing in some quantum chemistry and also some optimization performed on quantum computers. And some of this work is part of an open source software package called Masala, which my group developed in collaboration with Parisa's group.
Great, thanks. And last but not least, Parisa.
Hi, I'm Parisa. I'm assistant professor at North Campus, University of Oregon. And in this talk that I talked about, I mostly talked about cyclic K and how this method can replace the older method that exists there called GenCake. And yeah, Vikram also collaborated with us on that.
Great, good, thank you. All right, so let's jump right into it. So the first question is physics-based versus machine learning approaches. And so maybe I'll just put a little more meat on the bones there. You know, the panel can take this in any direction they really want to, but I thought it would be useful to really focus in on physics-based and ML approaches and how they differ in their contributions to quality, diversity, and speed of peptide designs. And what decisions do you think that the in the DMTA cycle would change, and how ultimately might hybrid approaches lead to accelerated test make test cycles? So Yu-Shan, I thought maybe we could start with you, because your work really incorporated elements of both, and in fact, you were able to leverage both and to a fairly impressive effect. So could you maybe start off with what you did in terms of using both, and how you think the interplay can be used to our advantage, and where do you think the things are going?
Mm-hmm. Yeah, so I mentioned molecular dynamic simulation, which can be very helpful at sample the fringe landscape of peptides that might not be well structured. However, we all know it's a trade-off between accuracy and speed. So molecular dynamic simulation, especially explicit solvent, is very, very slow and computationally expensive. So what the group has done is, by far we have simulated so many cyclic peptides, right? So then we could potentially bite the bullet once and then try to train a machine learning model using simulations of, say, hundreds of different sequences, so we can use the machine learning model to cover the whole sequence space. So we'll ask the machine learning model, hey, if I run a simulation, what do you think the results I will get? So this is, still not a very easy task. And then, so I do want to note that even I think it's a very promising approach. But if, say, Rosetta predicts this to be well-structured, I actually quite believe this will be well-structured, right? So then if those things exist, it could be great, right? But then we are just trying to be prepared. If we look at the cyclic peptide therapeutics, a lot of them are not well-structured. And then people think this ability to change conformations might be important for member permeability. We're just thinking, down the line, if you run into this situation, then you probably will need to use molecular dynamic simulation. Then how can we actually make it more efficient, or have models that we build by training ML on simulation data so we could get that information more efficiently.
Yeah, absolutely. I mean, one thing that really stood out to me is the physics-based methods are clearly powerful, but they are expensive and they can take some time. So I wondered if, Vikram, you're using a lot of physics-based methods, and what's your perspective on this?
Largely, I want to agree with what Yu-Shan said. I tend to be skeptical of end-to-end ML projects where you're supposed to just tell the ML model, this is what I want, and it's supposed to do all the work for you and produce a wonderful peptide. But we have found that ML is very useful in our work in many of the same ways, treating ML models as fast function approximators. If we have a slow but accurate way of doing something by physics-based methods, and we've done it many, many times, we also like to train ML models on the output of our past simulations so that we have a fast way of approximating them. One other thing I'll add to that is one idea that we've found to be useful when we're looking for a needle in a haystack and we're using simulation as a way of validating our possibilities. We want to minimize the number of simulations we have to do. And so one thing we've been doing is training ML models, knowing that they're going to make mistakes, they're going to have finite accuracy, and biasing the errors that they make towards false positives rather than false negatives. If you do this, then you can use your ML model to screen a large number of possibilities. Anything that it rejects is presumably a true negative. And then you can take the pool that it accepted and run your simulations on that much smaller pool. So you're not throwing away any of your needles in your haystack, but you're using the ML to greatly reduce the amount of computation you need to do to find those needles.
Yeah, no, I really like that. I think chemists always have a fear of missing out. And, when we, internally go to make a set of molecules for a project, that interplay in terms of, using the experimental data and the predictions to then select your next round of molecules to make is clearly where the field has already started and where we're headed. So, ultimately, I wonder, Vikram, do you have a perspective on how we might ultimately accelerate drug discovery by combining physics-based methods and machine learning tools? Yeah.
It's many small advances. I mean, I can tell you some of the things we're working on. Some of them include, now that we can do quantum chemistry calculations in the context of our pipelines, training ML models that approximate the quantum chemistry, training ML models that approximate the estimates of fold propensity of peptides. Parisa mentioned cyclic K, which is training ML models that can learn a latent space representation of the conformations accessible to a peptide.
Yeah.
I think one of the big things is trying to include more of a concept of both the conformational ensemble and the configurational ensemble in the design process. And that's very hard. The ultimate thing we would love to be able to do is find the sequence that maximizes the energy gap between the bound state and all of the possible configurations in the unbound state. And considering all those possibilities explicitly during a design calculation is impossible. So coming up with good approximations that let you do that implicitly, or kind of get at that calculation is the big challenge.
Right. Sounds like a good opportunity to maybe hand things off to Parisa to see what you might have to add to the conversation.
I think most of the important things that compares physics-based versus ML-based has been spoken. In our case, we noticed that the good thing about ML-based is that it's much, much, much faster than the other method. And it's something that helps us a lot when we want to then build side chains on it, of course. And another thing that we noticed is that the other method, the one that used before, was based on like 3 of its points needed to get calculated by needed to get calculated, but here we don't need that. And I think it's a promising thing that shows you how you can get a physics-based method that's good enough and then transfer it to make an ML model that's even better. But I would also say that the physics-based model is has to be there in my thinking. There needs to be a physics-based model first, and then we write the ML model to then make it better. But I don't know that without that physics-based, we can have the ML model, but it's my opinion. Yeah.
Okay, thanks. So I wanted to maybe just pass the ball to Hannes for a final word on this before we move on to the next topic.
Yeah, I guess so. The models that I built, they are more or less purely based on looking at data and then trying to replicate something that has been seen in that data and combining the patterns that have been seen in the data. And then hopefully the patterns that we observe in the data, they're also patterns that we might call close to physics or kind of generalizing, like for example, looking at physical chemical interactions. But then they're not like trying to go through the physics, trying to simulate the physics and roll them out, because we know that this takes a long time. So I see sort of machine learning approaches as the or deep learning approaches that also then learn from data in which we observe some physical patterns, and then hopefully we get away from overfitting on some patterns that confer less physical patterns, and then we're able to sort of, let's call it, emulate physics and have more abstract representations that are more higher level, but more efficient for making our inferences that still generalize and still can apply to a novel target or a novel type of binary that we want to produce.
Okay, great. And Stephen, do you have any final thoughts before we move on?
Yeah, mostly on the kind of design, make, test cycles and how we can use these tools in that context. We already sort of have tools, our co-folding tools, that are good for hit design, where we can pull bioactive sequences out of the computer and test them in a handful of designs and get a hit. But the other part of that is that hit to lead process. And I think that we haven't seen a lot of focused work on how do you take something where you have a lot more information, where you have a binder already, you have either a structure or an extremely highly confident model, and how do you help medicinal chemists make those decisions on what to make to optimize this to be a drug? And I think I'm excited to see how deep learning models can accelerate that aspect as well.
Great. Yeah, I agree. Quite exciting. All right, let's move on to the next topic, which is really the computational experiment interplay. And really, how does computation most effectively interact with experiments to rapidly identify starting points and progress our structural activity relationships? In other words, making analogs and progressing them towards a development candidate. Where have we already seen the computation meaningfully change the next design step, and where are the clearest unrealized opportunities? So maybe Stephen, maybe we'll start with you this time. You've done quite a lot in that space. Predictions that have been validated to a certain degree. by experiments and yeah, why don't you start us?
Yeah. I think that we've seen a huge increase in the success rate from computational design when it comes to binder design of cyclic peptides, which is extremely exciting. But I don't think it's a secret that those, in most cases, are not going to be drug-like molecules. They're all L. They lack a lot of the features that we can get out of peptide-based drugs. And so I think that the tools that we should be looking to build in tandem with trying to create these kind of all focusing models is just something that can work with those. And I think there's been some work already that was discussed with Parisa's work with heterochiral design using deep learning models and Vikram's work as well, and also Boltzgen, of course. So I think we're moving in the right direction, but having tools that can use all of the information that you get out of that hit instead of treating every problem like it is a de novo design problem when that's just not true. So yeah, I'm curious what other people's thoughts are on that.
Yeah, Hannes, maybe you could jump in here as well. You've done quite a lot of work in that space too with Boltzgen.
Yeah, I think these are like basically two problems, and both are extremely general, appear a lot. So with two problems, I mean, de novo designing something without any prior knowledge, like de novo designing a binder without any prior knowledge, and optimizing something existing. And this existing thing could be coming from a previous campaign that one did, or just from some other knowledge about some binder that we have, right? And now we are trying to build solutions and should be trying to build solutions for both because both appear all the time and are very fundamental across all of drug discovery. Yeah, I guess maybe not the most interesting comment here, but that's just my thoughts on the previous statements.
Yeah, I mean, are there ways that we can rapidly learn from experiments, or the computational approaches inform on the experiments? Are there ways for us to do less experiments? I mean, I think that's what we'd like to do ultimately,
Yeah.
because it takes some time and are expensive.
Okay, so maybe on the optimization side, I think oftentimes I get asked, I now have here this binder and this target, I already have 100 data points of affinity measurements. Can you fine tune your model on this to generate something? And then I would most of the time be like, no, I don't think that makes sense. I would rather try to directly develop some tools or machine learning models that are trained in general as sort of an improvement operator, where you across all data that we have, and then also in some generalizing fashion, instead of your 100 samples that you now have, across all data, we try to always train to be conditioned on an existing design and then generate something that's slightly better. And maybe you do that by making your existing good designs slightly worse, and then training and maybe some data augmentation schemes or something like that. And then you apply that to your existing binders, this sort of improvement operator, and then see that, or hope that this isn't just giving you some diversification or some reasonable diversification around your existing binder, but also actually an improvement.
Right. Good. Thank you. Maybe I'll pass the ball to Yu-Shan and ask for her opinion on this. And maybe I'll start you off with something. One of the impacts that I've seen here at Genentech is that the models don't necessarily, give us the answer, right? But what they're very good at is hypothesis generation, opening up, our minds in terms of like what things we should try, and that's led to some very interesting places. Do you have any comments in that regard, or, I mean, take things in another direction if you like?
Yeah. So, what these questions made me think about is, for example, when a collaborator approach us, right? So, usually, it will be preferred if they either have the structural information or they have some experimental data. For example, the lowest hanging fruit is like they already know what the protein-protein interaction interface they want to inhibit looks like. Then we can go after it by mimicking one of the partners, for example. And if they don't have the protein-protein interaction structural information, at least if they have the target structural information, that will also be helpful. And if they really don't have anything, then that can be hard because then you're relying on using AlphaFold or ZetaFold or both want to actually generate what the target structure should look like even. In those cases, then preferably you might have experimental data, right? So then you might actually have some screening data that actually says, oh, how I try these sequences and these are their binding affinity, so that we can try to verify the computational results, especially when we are not confident about the structural information of the target or the complex. I think this says something about unrealized opportunities. I think one thing that has been touched is about the computational platform's ability to handle non-canonical amino acids. So I think that will be very important if we are trying to be truly useful in peptide therapeutic developments. And the other one is I think we need to be able to handle more cyclization chemistries. So this, however, will make it very difficult to build on simply, for example, AlphaFold, because those are based on linear proteins. They do not have non-canonical amino acids and do not have weird cyclization chemistries that peptide drug developers might want to use. And I want to also mention from my own experience, I talk a lot about, simulations can provide you, the percent pre-organization for specific sequences, then we can rank them. I want to know one thing that is, it's not quantitative in the sense that we have run into situation we maximize the pre-organization. So we brought it up to, as high as we can, not a good binder at all. Because it doesn't translate into binding affinity in a quantitative sense, right? So then for peptide therapeutics, I think one area we are still lagging from small molecules is that we don't have free energy perturbation that works for flexible molecules like peptides. The other thing I think about how we can facilitate the process, given that mRNA displays can screen out, high affinity binder, I think one thing that could be very, very useful is if there is a computational tool that can predict passive member permeability. So this is another thing I think small molecules kind of have with their, rule of 5 or 2D descriptors, but then those don't work well for peptides. So I think if we can actually do that, that will really facilitate, be complementary to mRNA screening techniques, and then make our initial designs even more drug-like starting from the beginning.
Yeah, absolutely. That's a great point, and I think we'll address that in topic number 3. I thought, but you raised non-natural amino acids, and I think Vikram, you might have some thoughts on that as well.
Yeah, I like non-naturals. But broadly, thinking about the points that have been raised, one really important thing to keep in mind is that the fitness landscape for all the chemical entities that we might make. So if you imagine a space that arranges every possible molecule where the proximity between molecules is based on how chemically similar they are. And then at every point, you have a score associated with how good a drug this is for the task that you're doing. That landscape is incredibly rugged. A very small change in the chemical makeup of a molecule can have drastic impacts on its permeability, on its immunogenicity, on its propensity to favor a binding competent conformation. And for this, that problem is exacerbated with non-canonicals, because you can have you can have modifications that involve swapping out one atom for another, putting in a chloride in place of a hydrogen, which can completely change the binding or the conformational preferences. Because of this, I think it's very important to think of the problem of de novo design versus refinement as one where you want to get as close as possible to a fitness optimum in your de novo design stage, considering all of your objectives. Because even if you had the best refinement method in the world, something that perfectly rolls you down into the nearest local optimum, because the landscape is so rugged, the nearest local optimum is not necessarily going to be a very good optimum unless you're already very close to something that's terrific.
Mhm.
And this is actually one argument that I make for the not just physics-based methods, but the general optimization strategies that we use that are not ML based. They make it much easier to put in additional objectives that we want to optimize for during the initial sequence design. So we can incorporate not just energetic calculations to estimate binding affinity, but also additional constraints to promote permeability or to promote low immunogenicity or that sort of thing. But yeah, we tend to like problems where someone is not saying, I've got this peptide that's almost perfect. Can you introduce a very minor change to it to make it terrific? But rather where someone is willing to say, yeah, I'm okay with massive redesign to get into a deeper well in the fitness landscape.
Great. Thank you. Parisa, would you like the last word on this before we go to the next topic?
I think, sorry. I think all the important things was said before. In favor of Vikram and Yu-Shan because we the in the field of peptide design we can be far away from protein design. We can be completely different. And even like choosing what unnatural amino acids, for example, is important or can be important, even that would need a lot of thinking. And there are lots of unnatural amino acids that are out there. So I would say that in addition to all the correct things that they said, we need to also come up with a smart way of deciding which unnatural amino acids I want to use because they give us a lot of tools that just L-amino acids don't have. And I think that would be a very, very interesting to use. Yeah.
Yeah, no doubt. I tend to think of each side chain that's contacting a protein as its own small molecule to be optimized. And of course, you can't do that if you're sticking with natural amino acids. So clearly, a lot of work to be done to make sure that we can use non-natural amino acids at will, right, going forward. So exciting times. Let's move on to the final topic here. And Parisa, maybe we'll stick with you. Since your work really focused on generating structurally viable cyclic peptides, and from that vantage point, how do you think there is this disconnect between designing for binding versus designing for permeability as, two of the main problems that we have to solve, not the only ones, right? We have to solve for stability and DMPK properties and solubility and all these things at the same time. And, drug discovery is a multivariant problem, but maybe we just focus on two things that are super important, at least for intracellular targets or, achieving oral bioavailability. How can we do both at the same time? And, what's missing for us to optimize them in parallel?
Yeah, I can speak on that. So in terms of like binding, I think we are not too close, but we are very close to get the shape of binding at least true. In terms of permeability, I would argue that please define permeability for me. Is it going to membrane actively or passively? Does it interact with a receptor or not? Does it go through the bilayer of the cell by just randomly being pushed but don't have anything to the membrane? So there are several ways that the peptide can be permeable, and it's very hard to decide which one is the best one, honestly. So I would say that we get to binding first, and then permeability. It depends on what ways you want to choose your peptide to be. That's my take. I think maybe others have different thinking about that. But the more I learn about peptides, the more I think that binding will close, but permeability, we should think more about it. Yeah, that's my 2 cents. Yeah.
Yeah, I think you raised some great points, particularly around the multiple ways that a peptide can get into cells, and each one of those is probably a separate problem in of themselves. Not to mention that I'm sure that some peptides use more than one route of uptake. Maybe I'll pass things on to Stephen, maybe to continue on this conversation. One of the things that really stood out for me from your work is that, we're getting reasonably good at predicting peptides that can bind to targets with moderate affinity, and we're getting reasonably good at predicting peptides that can get into cells, but have no other function. How do we combine those two things together, and how far off are we?
Yeah, it's funny. Watching the field has been like two parallel tracks, and they're both kind of working, but like getting them to come back together has been really hard. So I would say we're at a point already where if we could even get slight activity and slight permeability, we'd be really excited. I think that using the kind of current level of co-folding deep models for binder design, not having at least experimentally validated access to N-methylation and even extremely hydrophobic designs, which we showed in the 2022 Cell paper, that was extremely important for at least passive permeability, which would be great. I think that trying, like, I guess as a anecdote, if I have a validated binder, if I mutate away all of the solvent exposed residues from likely lysines and glutamic acids to alanines, or other hydrophobic amino acids, there's a good chance that the prediction just fails now, because that's not the sort of thing that these models have seen in the PDB or whatever they're trained on. And so trying to force these models to design these greasy blobs as good starting points maybe isn't the right way to do this. And so my personal opinion right now in the field, if we were to use these models, what we should be doing is getting our hit and then trying to figure out with a combination of either new tools that are more focused on this problem, as well as the kind of experimental tools that we can use to just learn about the now class of molecules that we're trying to optimize. We're not exploring the whole space anymore. We kind of know what works. How do we make this permeable? And so I think that is one of the directions that we can do right now, as opposed to trying to pull permeable molecules that are also binders right off of the computer. I think that way we can also gain a lot of information that could then further be used later to optimize.
Great. Thanks, Stephen. Vikram, your thoughts on this?
Well, I know it can be done because it has been done. I wear two hats. I'm a Flatiron research scientist, but I also co-founded a company called Menton. And while there's a limit to what I can say about the project, Menton has designed peptides that in experiments have proved to be both permeable and bind to a target. This does get back to what I was saying earlier, though, about the importance of tackling multiple design objectives simultaneously during the initial design. But both objectives need to be encoded in the function you're optimizing. And intuitively, there are lots of reasons for this. Well, one of them is we know one of the factors that affects permeability is hydrogen bond donors on the backbone. If you have unsatisfied hydrogen bond donors that are happily interacting with water, and then you try and passively diffuse across a membrane, now those donors are no longer satisfied, and there's an energetic cost to desolvating them. But if you can N-methylate all of those, if you can remove them by some sort of chemical modification, N-methylation is a common one, you can eliminate that penalty. The trouble is that adding an N-methyl group greatly alters the conformational preference of an amino acid and greatly alters your overall conformational preferences of a peptide. So you have to include that. You can't do that in two separate steps. You can't say, okay, I've designed something that binds to my target, and now I'm going to stick in a bunch of N-methyls. You have to do simultaneous design to try to minimize the number of exposed polar groups on the backbone and design to maximize the number of favorable interactions with the target.
Yeah, no, I think that makes a ton of sense to me. You don't want to lock yourself into a binding mode where, there's a bunch of exposed hydrogen bond donors that, are necessary for binding. And if you get rid of them to improve permeability, well, then you lose the binding. And so you somehow have to find that Venn diagram of binding modes that are also compatible with permeability. Hannes, what are your thoughts?
I am mostly just listening and learning here, I think, about membrane permeability. But how I then would go ahead and try to, I guess, build first models toward this is to have something that does reason about sort of a dynamic process of interacting with the membrane and going through it, and then maybe training on lots of such simulations, and then trying to in paint sort of the thing that you need to make your transition happen from now being outside the cell to being inside the cell, or maybe trying to model what would need to change in your peptide to have the correct interaction with some solute carrier, if that is the right thing we need to interact with to get into to be or to permeate. And I'm not sure what the best approaches here are, or the right approaches. And maybe I don't know, maybe is it the case that in the end we shouldn't care about this problem and focus on designing AAVs that deliver our peptides? As I'm that ignorant about the difficulty of this type of delivery versus other delivery.
One thing you raised that I think hit on Parisa's comment about different modes of getting into the cell. Each one of those is, there's going to be different design rules for each one of those. Like a passively permeable molecule is going to be, one set of rules. Something like a stapled peptide, which seems to be more related to binding to the membrane and then internalized into the endosomes and then somehow achieving endosomal escape. That's going to be a separate rule. And I would suggest that we probably have to solve each one of those problems independently to a certain degree, to have a focused approach per scaffold. Anyways, those are my thoughts. Perhaps we can finish this question off with Yu-Shan and see what she has to add.
So I note that Parisa raised a question of what is definition of membrane permeability, right? So for a computational chemist, I think it's going to be extremely difficult to predict, if this peptide is going to hit a specific transporter or receptor and then go into cell. That's like maybe like a mission almost impossible for the next 5 years, I guess. So I think passive membrane permeability is probably what we might have a better chance, in the sense, like maybe model at least after some sort of lipid composition, right? So, but then recognizing the cellular membrane is very complicated. But then for small molecules, the heuristics are basically, trying to minimize hydrogen bond donors, trying to minimize hydrogen bond acceptors to a lesser degree, and have a balance between hydrophobicity and hydrophilicity. I have worked with collaborators. They were like, if you want me to choose between these two, always go for the hydrophobic one for peptides, because they typically are not so worried about water solubility, but they're very worried about membrane permeability. So then, the guideline is to choose whatever greasy thing that you can think of. And I think that it's currently so challenging because there is little information of what these peptides do in lipid-like environment. So what we are potentially fairly good at optimizing is the structure and binding in water. And then without the information of what these cyclic peptides would do in lipid-like environment, it makes it difficult to correlate membrane permeability with something easily. So I see this as a challenge, but then it's going to be very important if we want to make all stars align, or give some guidelines from the very beginning to see, what compositions or specific scaffolds that we should focus on.
Great. Good. Thanks, Yu-Shan. Great points. So we do have a couple of questions, maybe following nicely on the last discussion point. Charlie had a question. You want to get online, Charlie? Can you?
Hi, hello everyone. Yeah, sorry, I think you can read it, everybody in the comments, but largely, this is a great discussion on finding hits, and I believe, Hannes, you had this at the end of your presentation, that it's just the beginning of the story. And we just discussed the multiple mechanisms that could take place, but it seems that most of it is really early on in terms of just finding approaches to integrate for better processes. But what we really, I guess, need to focus in on is sort of, what, sorry, I just lost track. I was about to ask, I was rambling a bit, is it that people don't know what entry point they want to target? So what heuristics are we looking to apply? And is that the reason why we're not doing it? Or is it just because we're so focused on, kind of evolving the methods that we haven't really focused on this problem? So really bringing in the lessons learned from the different attempts to make things permeable, whether they're, from a sort of large perspective like proteins and then needing a formulation approach, or another delivery mechanism. That's something that we could probably follow on with a, kind of a PDHC seminar on that. But I was just broadly wondering what people are thinking about that. Is it that we're not disclosing what those are and they're not being discussed in the designs, or is it just the fact that they're so narrowly focused on the methods and improving them on the novelty and effectiveness of them? So that was a long-winded question, but hopefully it made sense.
Well, should I answer?
Vikram, maybe I'll direct it at you, because Menton, you used as an example where you've been successful, and I guess the question was, did you do both? Did you, what heuristics did you use? Was it for passive permeability or something else? And why is this not being done more?
Yeah, mainly, so I don't want to oversell that. Basically, it is one example in which we have been successful trying something very new. So the analogy I would use is we've built the right flyer and we've shown that it flew, but that doesn't mean that we've got commercial jet travel yet. We still have a lot of open questions about how well does this work? Does it work well enough on other targets? Does it? So they're applying it to another target now, seeing if it works. Yes, these methods will be published ultimately, but it's just very early days.
I think the important part there, and touching on some of the earlier discussion, was on the non-natural amino acids, because they bring not just the ability to bind better or differently, but really the properties that they bring to avoid some of the, kind of challenges with permeability, but also the druggability that Anthony mentioned about stability, for example, et cetera.
Yeah, there we have some established methods that are publicly available. A lot of them are in the Rosetta software suite. These also work to different degrees depending on how non-natural your non-natural is. The low-hanging fruit years ago for us was the D-amino acid mirror images of the canonical L amino acids because physics is symmetric. So those work very well. We can design very robustly with D-amino acids. Slightly more exotic side chains work pretty well. Our energy function isn't as good at those. It was one of the motivations for the project that I call macromolecule QM in my seminar. I think we're going to end up calling it Rosetta QM actually. It's something we're writing up now because quantum chemistry calculations are completely general and they don't have 1,000 parameters you have to tune for every new non-canonical. They're a very nice way to open up a lot of new chemistries. And also, if you want something faster than QM, they're a nice way to train QM, train force fields that you can use with non-canonicals. And the paper we're writing now, we show that we can pre-calculate Ramachandran maps for all sorts of non-canonicals. But basically, yeah, the more exotic the non-canonical, the harder it is. The less it looks like a canonical amino acid, the harder it is. Once you throw in non-canonicals that involve heavy elements, that becomes particularly hard, both for quantum chemistry and for ML methods, because we don't have examples of that in the databases, and because heavier elements just means more electrons for quantum chemistry.
Right. Vikram, maybe we'll just stick with you for a second. There was a question directed at you. I'll just read it off. Give me a second. I need to. Okay. Can you say more about, so this is from Pat Riley. Can you say more about the techniques you found to be effective in biasing models towards false positives over false negatives?
Yeah, this was a project that I worked on a while ago, and I need to get back to. Basically, the loss function that we used during the training of our model gave a bigger penalty for a false negative than for a false positive, and that ends up producing a model where more of the error is pushed into the false positives and less of it is in the false negatives. And any model is wrong. Some models are useful. Knowing that we're going to make error, we wanted to control where the error would be. So that was a trick that we used, and we found it worked pretty well. We were able in that particular project. I was trying to predict the propensity of given peptides to fold into a rigid structure, a value that we call p near that we can get from simulations, and although the ML model couldn't predict it with 100% accuracy, it could predict it well enough that we could reduce the number of simulations we'd need to find a hit by a factor of 5. And part of that was biasing the training, using a biased loss function during training, so that the model was more likely to overestimate rather than underestimate the value of p near.
Right. Great. I think we probably have time for one more question, and here's one that really stuck out to me. We talked about the permeability challenge and trying to satisfy both binding and permeability at the same time. It seems to me that one of the challenges we have in the permeability space is access to large data sets, experimental data sets that really speak to whether peptides are permeable or not. So the question in this regard is, does the panel have a favorite set of high throughput experimental approaches to probe, well, not only permeability, but also solubility? I think solubility was mentioned because it's clear that one of the easy ways to achieve a degree of permeability is just through having fairly greasy peptides. But what inevitably happens, or happens quite often is that those very hydrophobic peptides just don't have any solubility or have very poor drug-like properties. They can do nasty things to membranes, that type of thing. So trying to find a hydrophobic molecule that also somehow has better than predicted solubility, something like cyclosporin A, right? Very greasy molecule, but still has some reasonable solubility. So ultimately, what are the approaches that we should be focusing on to collect large sets of permeability and solubility so that we can train computational approaches? So I'll leave that open for
I
Parisa, maybe.
can
Yeah, go ahead.
probably go first. So one of my students actually start with the idea that she's gonna make 96 peptides based on some analysis and then test it on Pampa to get the Pampa information that we need and then bring it to Keiko2 or something. And while running Pampa, she realized that how many hours you put them, what is the day, how long do you let the peptide stay in top. All of these has effects that it wasn't reported, but everyone uses some set of Pampa parameters, and every one of those things are different because they use a different metric. So in terms of so basically her paper is gonna come out soon, but she showed that we don't know enough even about Pampa, and basically she suggested that you need to find a way, or everybody needs to find a way to run Pampa the same way if they want to run it. So it was a little sad, but at least we have now this knowledge that Pampa doesn't work the way we want. So this is something that I think we should take into account. And for any active or passive routes that we want to check, to base on that, make this permeability, we should maybe decide that all of us run the same protocol so that then the peptides, then we can write a very good technique on all the samples. Because if they are different, then writing a model wouldn't be really easy.
Yeah. Stephen, you've done some work on the permeability question. Maybe we'll give you the last word on this because we're almost at time.
Yeah, I definitely agree with what Parisa said. I mean, there's a lot of variability in those results, lab to lab. And I think that makes getting a clean data set difficult, such that most of these models or anything you're trying to build would be very internal and very specific to your process. It's also difficult because you don't want to necessarily throw away something that doesn't work in Pampa as your first screen, when if you had gone to a cell assay, for reasons we don't understand, it does have some activity and is potentially optimizable. So I think it is worth taking a lot of these things with a grain of salt. And if you have something that, isn't unlikely to have any chance of going across a membrane, maybe it is worth testing in a high throughput assay, cell-based assay.
Right. Good. Well, perfect timing. Right on time here. So I wanted to thank the panelists not only for their excellent talks, but their engaging discussions here. I learned a lot, and I hope everyone had a enriching hour here. We will be doing more of these, so please stay tuned, and thanks to the audience for attending as well. So I think we'll sign off there, and yeah. Thanks everybody once again.
Thank you, everyone. The meeting was recorded, and I will send out the meeting summary that AI took. And I will circulate the chat because there were some questions that we didn't get to. So it would be great we can always continue offline email with the questions.
Perfect.
Thank you, everyone.
Thanks, everyone.